Hello and welcome back. It's finally Christmas and I'm going to make a Christmas special. Specifically in this video I'm going to talk a bit about metric tenses, maybe in the Minkowski space, I don't really know. But you may be wondering why I haven't made so many videos in the last time, and that's because I spent time learning this. I'm so sorry. But I also think I'm going to initialize a new series about Riemannian spaces and things like that. So let's dive right in. So in Cartesian coordinate systems, we define the natural basis of the three-dimensional Euclidean space to be the basis triplets. That's to say, I hope you can see, x1 equals 1, 0, 0, x2 equals 0, 1, 0, and x3 equals 0, 0, 1. And then any element x, where x is equal to x1, x2, x3, an element of the Euclidean space, R03, is expressed as a linear combination of the basis triplets x equals xj, xj, where j equals 1, 2, 3. We can easily verify that xj dotted with xk equals the Kronecker delta. And yeah, the linearity of the inner product implies that x dot y equals xj, x hat j dotted with yk, x hat k equals xj yk, x hat j dotted with x hat k equals the Kronecker delta times xj yk. In general, the inner products of the basis elements of an inner product space V determine a matrix with elements g, jk equals xj dotted with xk. And the matrix GJK is called the metric tensor of V. Hence, the metric tensor of the Euclidean space R03 in Cartesian coordinates is the identity matrix I. That is, the matrix of GJK equals the matrix of the Kronecker delta. By definition, is equal to I. But what about the metric tensor of the three-dimensional Minkowski space? Well, in the Minkowski space, R1, 3, the matrix elements of the metric tensor in Cartesian coordinates are determined by the relationships xj dotted with xk equals 0 if j is not equal to k, and x1 dotted with x1 equals 1, x2 dotted with x2 equals 1, and x3 dotted with x3 equals minus 1. Hence, the metric tensor of the Minkowski space in Cartesian coordinates is determined by the matrix G. By definition, is equal to the matrix of GJK equals 1, 0, 0, 0, 1, 0, 0, 0, minus 1. Follows quite easily. And then, in any case, the metric tensor is symmetric. By definition, in Riemann spaces, the inner product is positive defined, but in Minkowski or Einstein spaces it's not. The inverse matrix of GJK is symbolized by G, J, K with superscripts. It holds that G, J, K dotted with G, K, N subscripts is the identity, and G, J, K times G, K, N is the Kronecker delta with subscript N and superscript J. We define the norm in point X in an inner product space by the relationship the norm of X by definition is equal to the square root of the dot product of X and X is equal to the square root of G, J, K times xj k xk. Sorry. Yeah, and the distance d of x and y between 2 points x and y of the space with norm is defined as follows. This is equal to, by definition, is equal to the norm of x minus y is equal to the square root of x minus 1 dotted with x minus y. We notice that the measurement of distances in the space with norm, as well as the calculation of distances between points on curves or surfaces immersed in this space, is possible only if we know the metric tensor g of x of the underlying space. And we need to make a small remark. So we could get an abstraction of the idea of the Euclidean space as follows. Consider a set V of points, whatever these points could be, and such there is a 1-1 correspondence of V on the triplets of the Euclidean space R03. Then the structure of R03 is projected on V, and we could claim that V is the three-dimensional Euclidean space. Assume that the points of R03 are determined in Cartesian coordinates. Name O the point of V corresponding to the triplet O. We could call the origin of V. Then name P1, P2 and P3 the points of V corresponding to the triplets. Namely x1 equals 1, 0, 0, x2 equals 0, 1, 0, and x3 equals 0, 0, 1. All an element of R03. The origin O and the points P1, P2, P3 of V determine a Cartesian coordinate system on V. And that's the beginning of a pretty long series, I think, on Riemannian geometry. I hope you all have a very Merry Christmas, and I don't know. See ya!